Welcome back to For Science Salah Lotfy channel. In today's episode, I'm diving into the fascinating world of plasma sheaths and double layers, two crucial concepts that control how plasma interacts with boundaries and itself. These phenomena are not just theoretical, they have practical implications in various fields, from space exploration to industrial applications. Let's kick off with the plasma sheath. This is a thin, non-neutral layer that forms between a plasma and a solid surface like a wall or an electrode. It's a critical region where the properties of the plasma change dramatically. Why does it form? Well, electrons are much lighter and faster than ions. This difference in mass and speed leads to a separation of charges. They rush toward the walls, leaving behind a positively charged region in the plasma. This charge separation is the key to understanding the formation of the sheath. This imbalance creates an electric field that slows down further electron loss, and that's how the sheath is born. This electric field is crucial for maintaining the stability of the plasma. But not just any sheath can form. For a sheath to be stable, the ions at its edge must move faster than a certain threshold, called the Bohm criterion. This criterion ensures that the sheath can sustain itself without collapsing. The ion speed at the sheath edge must be at least the ion acoustic speed, which is the square root of electron temperature divided by ion mass. This relationship is fundamental in plasma physics. This ensures that ions are accelerated smoothly toward the wall, while electrons are held back. The sheath acts as a gatekeeper, regulating the flow of particles. There are two major types of plasma sheaths. First, the collisionless sheath, which appears in low-pressure plasmas where particles rarely collide. This type of sheath is often found in the vast expanse of space. This type is common in space or laboratory plasma experiments. Scientists study these sheaths to understand space weather and other cosmic phenomena. Then we have the collisional sheath, found in higher pressure environments where frequent collisions affect particle motion and energy distribution. These sheaths are more common in industrial applications. So what does a sheath actually do? It maintains an electric potential drop that repels most electrons while allowing ions to accelerate toward the surface. This potential drop is essential for many plasma processes. This drop typically spans a few dB lengths, a measure of how far electric fields penetrate a plasma. The dB length is a fundamental parameter in plasma physics. And when current is involved, the Child-Langmuir law helps us understand how space-charge limited currents behave inside the sheath. This law is crucial for designing devices that use plasma. Next up, double layers. These are fascinating structures that occur within the plasma itself. They are like mini sheaths that form within the bulk of the plasma. A double layer consists of two adjacent regions with opposite electric charge. This creates a sharp potential drop within the plasma. This forms a sudden potential drop and acts like an electric barrier. It can influence the movement of particles and energy within the plasma. These layers are common in space, think auroras and solar flares. But we also find them in laboratory plasmas and electric propulsion systems. They play a role in many natural and engineered systems. They often arise due to instabilities in the plasma or local charge separation. These instabilities can lead to fascinating and complex behaviors. Interestingly, double layers behave like diodes, allowing current to flow easily in one direction but resisting flow in the opposite direction. This diode-like behavior is useful in many applications. Why should we care about these plasma structures? Plasma sheaths are vital in plasma etching, thrusters, and fusion reactor design, especially where plasma touches a material surface. They are essential for controlling the interaction between plasma and materials. Controlling the sheath means controlling ion energy, which is key in high-precision applications. This control is crucial for achieving desired outcomes in various technologies. Meanwhile, double layers help explain particle acceleration, electric propulsion, and various astrophysical phenomena. They are fundamental to our understanding of many high-energy processes. They also serve as diagnostic tools for understanding plasma behavior. By studying double layers, scientists can gain insights into the conditions and dynamics of plasmas. Behind the scenes, scientists model sheaths and double layers using equations like Poisson's equation, which relates electric potential to charge distribution. These models are essential for predicting plasma behavior. They use kinetic and fluid models to simulate these structures under different plasma conditions, helping us predict behavior in both the lab and in space. These simulations are crucial for advancing our understanding and technology. To sum up, plasma sheaths are boundary layers that regulate charge flow between plasma and walls. They are essential for maintaining the stability and functionality of plasma systems. The Bohm criterion determines if a sheath can form. This criterion is a fundamental aspect of plasma physics. Double layers are internal structures with a sharp potential drop, essential in many natural and engineered plasma systems. They play a crucial role in the behavior and application of plasmas. These phenomena are modeled mathematically and are crucial in both research and real-world applications. Understanding them helps us harness the power of plasma for various technologies. Thanks for joining me on this deep dive into plasma sheaths and double layers. I hope you found it as fascinating as I do. Special thanks to our viewers for your continued support. Your interest and enthusiasm keep us going. Don't forget to like, share, and subscribe, and leave your thoughts and questions in the comments below. We love hearing from you and engaging in scientific discussions. Stay curious, and keep exploring with For Science Salah Lotfy channel. Hey science enthusiasts! Ever wondered how waves travel through the mysterious medium of magnetized plasma? It's a fascinating journey that takes us from the depths of space to the laboratories on Earth. Today I'm going to unlock some of those secrets. We'll explore the unique properties of plasma and how it behaves under the influence of magnetic fields. Buckle up as we dive into the fascinating world of plasma physics. This isn't just any ordinary science lesson, it's an adventure through the very fabric of the universe. First off, plasma isn't just any hot gas, it's the fourth state of matter, distinct from solids, liquids, and gases. It's an ionized medium, which means it's packed with charged particles that can support both electrostatic and electromagnetic waves. These particles are in constant motion, creating a dynamic and complex environment. When a magnetic field is in the mix, things get really interesting. The interaction between the magnetic field and the charged particles leads to a variety of wave phenomena that are both intriguing and essential for many applications. Imagine plasma behaving in ways ordinary fluids could never dream of. The presence of a magnetic field can cause the plasma to exhibit behaviors that are counterintuitive and fascinating. The key player here is something called the dielectric tensor. This mathematical construct helps us understand how the plasma responds to electric fields. It's like a cheat sheet that tells us how electric fields interact with the charged particles in plasma. By understanding the dielectric tensor, we can predict how waves will propagate through the plasma. This depends on factors like plasma density, magnetic field strength, and wave direction. Each of these factors can significantly alter the behavior of waves in plasma. Now let's talk about the Appleton-Hartree formula. This formula is crucial for understanding wave propagation in magnetized plasma. This formula gives us the index of refraction for waves traveling through cold magnetized plasma. It helps us determine how waves bend and change speed as they move through the plasma. It predicts two modes of propagation: the ordinary mode, unaffected by the magnetic field, and the extraordinary mode, which the magnetic field profoundly influences. These modes are fundamental to understanding how waves behave in different plasma environments. These modes have different cutoff frequencies. The cutoff frequency is the point below which waves cannot propagate through the plasma. Under certain conditions, waves simply can't propagate. Next up, resonance. Resonance occurs when the frequency of a wave matches a natural frequency of the plasma. When a wave's frequency matches a natural frequency of the plasma, we get resonance. This can lead to significant energy transfer and amplification of the wave. Take cyclotron resonance, for example. This phenomenon occurs when the wave frequency equals the electron or ion's rotation frequency in the magnetic field. It happens when the wave frequency equals the electron or ion's rotation frequency in the magnetic field. This resonance is crucial for many plasma applications, including heating and diagnostics. Plasma particles absorb energy efficiently at these resonances, which is crucial for heating plasma in fusion research. This energy absorption is a key factor in achieving the conditions necessary for nuclear fusion. And then there's Faraday rotation. This effect occurs when linearly polarized waves move along a magnetic field, causing their polarization plane to rotate. When linearly polarized waves move along a magnetic field, their polarization plane rotates. This rotation is due to the different speeds of the left and right circularly polarized components of the wave. This is because left and right circularly polarized components travel at different speeds. Understanding this effect is essential for interpreting radio signals from space and satellite communications on Earth. It helps us decode the information carried by these signals and improve our communication technologies. Let's meet Whistler waves and Alfvén waves. These waves are fundamental to our understanding of space weather and plasma dynamics. Whistler waves are low-frequency waves traveling along magnetic field lines detected in Earth's magnetosphere, helping us study space weather. They provide valuable insights into the behavior of the Earth's magnetic field and its interaction with solar wind. Alfvén waves, on the other hand, are MHD waves where magnetic tension acts like a spring, carrying energy along magnetic field lines, crucial for understanding solar wind and auroras. These waves play a significant role in the transfer of energy and momentum in space plasmas. In many cases, we assume a cold plasma, ignoring thermal motion, which simplifies things but gives us deep insights into wave behavior. This assumption allows us to focus on the fundamental interactions without the complications of thermal effects. However, in real-world applications, warm plasma effects matter. The thermal motion of particles can significantly influence wave propagation and energy transfer. Kinetic theory helps us understand phenomena like Landau damping, where wave energy is transferred to particles. This damping effect is crucial for understanding how energy is dissipated in plasma. So why does all this matter? Understanding wave behavior in magnetized plasma is essential for a wide range of applications, from energy generation to communication technologies. Wave behavior in magnetized plasma underpins fusion energy research, where radio waves heat and control plasma, ionospheric communications, and even astrophysical investigations from the solar corona to interstellar plasmas. These studies help us unlock the secrets of the universe and develop new technologies. From Earth's ionosphere to distant galaxies, waves in magnetized plasma unlock the secrets of energy, space, and motion. They provide a window into the processes that shape our universe. If you found this intriguing, give it a like, share it with fellow science lovers, and let me know your thoughts in the comments below. Your engagement helps us bring more exciting science content to you. Until next time, stay curious. Keep exploring, keep questioning, and keep the spirit of discovery alive. We often learn about three states of matter: solid, liquid, and gas. These are the forms we encounter in our daily lives, from the ice in our drinks to the air we breathe. But the universe is far more complex and fascinating than just these three states. But there's a fourth state, a state that dominates the cosmos: plasma. Plasma is not something we encounter every day on Earth, but it makes up more than 99% of the visible universe. From the stars in the night sky to the glowing nebulae, plasma is everywhere. Plasma is essentially a gas that has been superheated and ionized. This means that the gas particles have been energized to the point where electrons are stripped away from their atoms, creating a soup of charged particles. Picture this. Atoms, stripped of some of their electrons, are zooming around at incredible speeds, colliding with each other and creating a chaotic yet mesmerizing dance of charged particles. This dynamic state is what gives plasma its unique properties, such as its ability to conduct electricity and generate magnetic fields. This energetic state of matter is what powers the stars, including our very own sun. The sun's surface is a seething mass of plasma, with temperatures reaching millions of degrees. Solar flares and coronal mass ejections are dramatic demonstrations of plasma activity. Fusion, the process that makes stars shine, occurs within these plasmas. In the core of stars, immense pressure and temperature force hydrogen nuclei to fuse together, forming helium and releasing vast amounts of energy. It's a nuclear reaction where light atomic nuclei, like hydrogen isotopes, fuse together to form heavier ones like helium, releasing tremendous amounts of energy in the process. This energy is what makes the stars, including our sun, shine so brightly. Replicating this stellar process on Earth holds immense potential for clean and sustainable energy. Scientists are working tirelessly to develop fusion reactors that can harness this power, promising a future where we can generate electricity without the harmful byproducts of fossil fuels. Imagine a future where power plants harness the same energy source that fuels the stars, providing us with a nearly limitless supply of clean electricity. This could revolutionize our energy systems, reducing our reliance on non-renewable resources and mitigating climate change. But there's a catch. Creating and controlling these miniature suns here on Earth is a formidable challenge. The conditions required for fusion are extreme, and maintaining a stable plasma is no easy feat. It's like trying to hold a star in a bottle, and that bottle needs to be invisible. Scientists use powerful magnetic fields to contain the plasma, preventing it from touching the reactor walls and losing its energy. This is where plasma confinement and heating come in. advanced technologies are being developed to heat the plasma to the necessary temperatures and keep it stable long enough for fusion to occur. The journey to harnessing fusion energy is challenging, but the potential rewards are immense. Imagine trying to hold a tiny, incredibly hot sun in your hand. It sounds impossible, right? That's the challenge with plasma. It's so hot that it would melt any material we know of. To make fusion a reality, we need to find a way to contain this superheated plasma and keep it stable long enough for fusion reactions to occur. Think of it like this. We need to create a container that can withstand temperatures hotter than the sun's core without actually touching the plasma itself. It's like a cosmic balancing act, where we need to use clever techniques to suspend the plasma in a delicate equilibrium. This is where the ingenuity of scientists and engineers comes into play. They have devised two main approaches to confine and heat plasma: magnetic confinement and inertial confinement. Each approach has its own set of challenges and triumphs, but both hold the key to unlocking the power of fusion energy. Magnetic confinement is like using invisible force fields to trap the plasma. Remember, plasma is made of charged particles, and charged particles, like tiny magnets, are affected by magnetic fields. So, scientists have devised ingenious ways to create powerful magnetic fields that can confine and control the plasma, keeping it from touching the walls of the reactor. One of the most promising magnetic confinement devices is called a tokamak. Picture a giant donut-shaped chamber surrounded by powerful electromagnets. These magnets create a magnetic field that acts like an invisible cage, trapping the plasma within the donut's hollow center. The plasma whirls around inside this magnetic bottle, heated to incredible temperatures. Another type of magnetic confinement device is called a stellarator. Instead of a simple donut shape, a stellarator has a more complex, twisted shape. This twisted shape creates a magnetic field that is even more effective at confining the plasma, potentially leading to more stable and efficient fusion reactions. Section 4. Inertial confinement, a dance of lasers and fuel pellets. Inertial confinement takes a different approach. Unlike magnetic confinement, which uses magnetic fields to contain the hot plasma, inertial confinement relies on the sheer force of laser or particle beams to achieve the necessary conditions for fusion. Imagine shining a powerful laser pointer on a ping-pong ball from all directions at once. The idea is to create an immense amount of pressure on the surface of the ball, forcing it to collapse inward. The pressure from the laser light would cause the ping-pong ball to implode or collapse in on itself. This implosion is key to achieving the high temperatures and pressures needed for fusion. Inertial confinement fusion works in a similar way, but on a much smaller and more energetic scale. Instead of a ping-pong ball, we use tiny pellets of fusion fuel. These fuel pellets are typically a mixture of deuterium and tritium, which are isotopes of hydrogen. Deuterium and tritium are chosen because they have a higher probability of fusing together under the right conditions. These fuel pellets are about the size of a grain of sand. Despite their small size, they hold the potential for immense energy release. Powerful lasers or particle beams are focused on the fuel pellet from all directions simultaneously. This precise targeting is crucial to ensure uniform compression of the pellet. This intense bombardment ablates or vaporizes the outer layer of the pellet, creating a rocket-like effect that compresses the fuel inside. The ablation process is essential for achieving the necessary compression. This compression heats the fuel to extreme temperatures and densities, causing the nuclei to overcome their natural repulsion and fuse together, releasing a burst of fusion energy. This energy release is the ultimate goal of inertial confinement fusion, promising a potential source of nearly limitless and clean energy for the future. Section 5. Igniting the fire, heating the plasma to stellar temperatures. We've talked about confining the plasma, but how do we heat it up to the scorching temperatures needed for fusion to occur? This is one of the most challenging aspects of achieving nuclear fusion. The temperatures required are not just high, they are astronomical. We're aiming for millions of degrees Celsius, far beyond anything we encounter in everyday life. Remember, we're talking about temperatures hotter than the core of the sun. The sun's core reaches about 15 million degrees Celsius, but in a fusion reactor we need to achieve even higher temperatures to overcome the repulsive forces between atomic nuclei. One method is called ohmic heating, which is similar to how an electric stove works. In this process, a strong electric current is passed through the plasma. The plasma's natural resistance to this current causes it to heat up, much like how the coils of an electric stove glow red hot when electricity flows through them. A current is passed through the plasma, and the electrical resistance of the plasma causes it to heat up. This method is effective up to a point, but to reach the extreme temperatures needed for fusion, additional heating methods are required. Another method is called neutral beam injection. This technique involves firing high-energy neutral atoms into the plasma. These atoms are neutral so they can penetrate the magnetic fields confining the plasma. Think of it like firing tiny, super-fast bullets of neutral atoms into the plasma. When these high-speed atoms collide with the plasma particles, they transfer their energy, effectively heating the plasma. These neutral atoms collide with the plasma particles, transferring their energy and heating up the plasma. This method is particularly useful for adding energy directly to the core of the plasma, where it's most needed. Finally, there's radio frequency heating. This method uses electromagnetic waves to transfer energy to the plasma. It's akin to how a microwave oven heats up food by causing water molecules to vibrate. This method uses radio waves to transfer energy to the plasma, much like a microwave oven heats up food. The radio waves are carefully tuned to match the natural frequency of the plasma particles. The radio waves are tuned to a specific frequency that resonates with the plasma particles, causing them to absorb energy and heat up. This resonance effect ensures that the energy is efficiently transferred, helping to achieve the necessary temperatures for fusion. Plasma, often called the fourth state of matter, is a fascinating and complex phenomenon that continues to intrigue scientists. It exists everywhere in the universe, from the heart of stars to the neon signs we see every day, illuminating our nights. Understanding plasma is crucial for a variety of scientific fields, including astrophysics, fusion energy research, and material science, each relying on its unique properties. But studying plasma is not easy, as it presents numerous challenges. Unlike solids, liquids, and gases, plasmas are composed of charged particles, ions, and electrons that interact with electric and magnetic fields, creating complex behaviors. This makes them incredibly dynamic and challenging to analyze, requiring sophisticated techniques. This is where plasma diagnostics come in, providing essential insights. Plasma diagnostics encompass a range of techniques used to measure the fundamental properties of plasma, such as temperature, density, and the strength of electric and magnetic fields within it, offering a window into its behavior. These techniques provide scientists with the crucial data needed to unravel the mysteries of plasma behavior, enabling further advancements. The information gleaned from plasma diagnostics is not just theoretical, it has practical applications in various fields, impacting technology and industry. In fusion research, for example, diagnostics are essential for monitoring and controlling the superheated plasma within experimental reactors, ensuring safety and efficiency. Similarly, in space physics, diagnostics help us understand the behavior of the solar wind and its impact on Earth, protecting our planet from potential hazards. One of the most fundamental and widely used plasma diagnostic tools is the Langmuir probe. Named after its inventor, Irving Langmuir, this deceptively simple device provides valuable information about plasma properties. The Langmuir probe consists of a small metallic electrode, often a wire, inserted directly into the plasma. By applying a voltage to the probe and measuring the resulting current, scientists can determine key parameters such as electron temperature, electron density, and plasma potential. The principle behind the Langmuir probe lies in the interaction between the probe and the surrounding plasma. When a voltage is applied, the probe draws in charged particles from the plasma, creating a region around the probe known as the sheath. The size and characteristics of this sheath depend on the plasma properties and the applied voltage. Langmuir probes have found widespread applications in various plasma research areas. They are commonly employed in low-temperature plasma processing, where they help optimize conditions for etching, deposition, and surface modification. Additionally, Langmuir probes play a crucial role in fusion research, providing real-time measurements of plasma parameters within experimental reactors. While the Langmuir probe is a powerful tool, it has limitations, particularly in plasmas with high plasma potentials. These limitations can affect the accuracy and reliability of the measurements, especially in dynamic plasma environments. This is where the double probe method comes in, offering a more robust solution for such challenging conditions. As its name suggests, the double probe utilizes two identical probes inserted into the plasma, effectively eliminating the need for a reference electrode. This setup simplifies the measurement process and enhances the accuracy of the data collected. The two probes in a double probe setup are biased with respect to each other, and the current flowing between them is measured. This method allows for precise control and monitoring of the plasma characteristics. By varying the bias voltage, scientists can obtain a characteristic curve that provides detailed information about the electron temperature and density of the plasma. This data is crucial for understanding plasma behavior. The advantage of the double probe method lies in its insensitivity to fluctuations in plasma potential, making it suitable for use in a wider range of plasma environments compared to the single Langmuir probe. This robustness is particularly beneficial in unstable or varying plasma conditions. Double probes find applications in various plasma research areas, including the study of space plasmas. Their versatility makes them an essential tool for scientists exploring different plasma phenomena. Mounted on satellites and rockets, double probes have been instrumental in characterizing the properties of the Earth's ionosphere and magnetosphere, providing valuable data about the interaction between the Sun and our planet. This data helps in understanding space weather and its effects on Earth. Furthermore, double probes are used in laboratory settings to investigate the behavior of low-temperature plasmas, contributing to advancements in fields like plasma processing and material science. These studies are essential for developing new technologies and materials. Section 4. Light reveals all spectroscopic diagnostics in plasma research. Spectroscopic diagnostics offer a powerful and versatile approach to probing the secrets of plasma, a state of matter that is both fascinating and complex. By analyzing the light emitted, absorbed, or scattered by plasma, scientists can gain insights into a wide range of plasma properties, including temperature, density, composition, and even magnetic field strength. This information is crucial for both fundamental research and practical applications. One of the key techniques in spectroscopic diagnostics is the analysis of spectral line intensity, which provides detailed information about the plasma's characteristics. Atoms and ions within the plasma emit light at specific wavelengths, creating a unique spectral fingerprint that can be analyzed to determine various properties. The intensity of these spectral lines is directly related to the population of excited states in the plasma, which in turn depends on the plasma temperature and density. This relationship allows scientists to make precise measurements. Another valuable technique is Doppler broadening, which exploits the Doppler effect to determine the temperature of particles in the plasma, providing another layer of diagnostic capability. The random thermal motion of ions and atoms in the plasma causes a broadening of the spectral lines, which can be measured and analyzed. The wider the lines, the higher the temperature of the particles, making this a direct method to gauge thermal conditions within the plasma. Furthermore, the Zeeman effect, which describes the splitting of spectral lines in the presence of a magnetic field, provides a way to measure the magnetic field strength within the plasma, adding another dimension to the analysis. By analyzing the separation between the split lines, scientists can map out the magnetic field structure and strength, offering insights into the magnetic environment of the plasma. Finally, stark broadening arises from the interaction of emitting atoms or ions with electric fields in the plasma, which can significantly alter the spectral lines. By analyzing the shape and width of spectral lines affected by stark broadening, researchers can infer information about the electric field strength within the plasma, completing a comprehensive diagnostic toolkit. Section 5. Microwaves to the rescue: interferometry and electron density. Microwave interferometry is a widely used diagnostic technique for measuring the electron density in plasmas. This technique relies on the interaction of microwaves with the free electrons present in the plasma. In microwave interferometry, a beam of microwaves is passed through the plasma, and the phase shift of the beam is measured. The presence of free electrons in the plasma causes a change in the refractive index of the medium, leading to a phase shift proportional to the electron density. By carefully measuring this phase shift, scientists can accurately determine the electron density profile across the plasma. Microwave interferometry is particularly well suited for diagnosing high-density plasmas, such as those found in fusion experiments, where other techniques may be less effective. Its non-invasive nature makes it ideal for monitoring plasma parameters without disturbing the delicate balance within experimental setups. Section 6. Lasers at work. Advanced techniques for plasma analysis. Lasers have revolutionized many areas of science and technology, and plasma diagnostics are no exception. Laser-based techniques offer unparalleled precision and sensitivity, allowing scientists to probe plasma properties with unprecedented detail. One such technique is laser-induced fluorescence, or LIF, a powerful tool for measuring plasma parameters such as temperature, density, and flow velocity. In LIF, a laser is tuned to excite a specific atomic or molecular transition within the plasma. The excited species then decay back to their ground state, emitting photons that are detected and analyzed. By carefully selecting the excitation and detection wavelengths, scientists can isolate the fluorescent signal from background noise, enabling highly sensitive measurements. Another powerful laser-based technique is Thomson scattering. This technique relies on the scattering of laser light by free electrons in the plasma. By analyzing the spectrum of the scattered light, scientists can determine the electron temperature and density with high accuracy. Thomson scattering is particularly well suited for diagnosing high-temperature plasmas, such as those found in fusion experiments where other techniques may be challenging to implement. As we conclude today's episode, For Science, Salah Lotfy channel would like to extend its deepest thanks and appreciation to Professor Dr. Tarek Nagla, a distinguished scientist and academic in the field of nuclear and radiation engineering, for his continued scientific support to our channel. His guidance and contributions have been instrumental in shaping the quality and depth of the content we share with you. We also express our sincere gratitude to our dedicated followers and viewers. Your engagement drives us forward. We'd love to hear your thoughts. Please leave a comment on the video below. Thank you for watching, and stay curious. For Science, Salah Lotfy channel.